Last time we talked about first order reactions, and we'll summarize that in a little bit. This time we're going to talk about second order reactions. Both of these together comprise about 99% of all chemical reactions, at least when we're talking about the elementary reactions that go into overall mechanisms. So to summarize from last time, a first order reaction is something with an elementary reaction that looks like this. It doesn't matter what the products are, there can be more than one. But it does matter that there's only one reactant on the reactant side, and then there's an equilibrium, or not an equilibrium constant, a rate constant K. The rate equation is then minus dA dt equals K times A. And then there's a relationship between the reactants and products, between the rates for reactants and products, which is also useful. We solve both of these differential equations basically by separating the variables and integrating on both sides. And if we do that with this relationship, then we get that the concentration of A plus the concentration of P has to equal a constant, which turns out to be the concentration of A at time 0. And if we solve the other differential equation, then we get that A is an exponentially decaying function, which has lots of implications, as was pointed out last time. We can combine these two relationships in order to get together with this one, in order to get the way that the product changes with time. And then we get basically that it's equal to the reactant, the initial reactant concentration minus the reactant as a function of time. And that gives rise to a pair of curves that looks like this. The reactant is decaying away, right? This is an irreversible chemical reaction up here. The A species, the reactant species, can go away, but it can never come back. The product species can build up, but it can never go away, and so we're going to get a monotonically decreasing concentration of A and a monotonically increasing function of P. By looking at those graphs, you can't tell that it's exponentially decaying, and that's an important property. How do you tell? One way is to use this form for to basically take the log of both sides of this. And then notice that that means that if you plot the log of A versus T, that should give you a straight line. The slope of that straight line is minus K. The intercept for that straight line on the y-axis is the logarithm of the initial A concentration. Another unique property for first-order reactions is that if you solve for the half-life, it doesn't depend on the initial concentration. It's just log 2 divided by K, which means that knowing the half-life is essentially the same as knowing the rate constant and vice versa. So it's an easy way to sort of measure the rate constant or vice versa. And also it means you can rewrite the integrated rate equation in this form, where now the base for the exponential decay is 2 rather than E, and that's useful. It basically means that as things are decaying, it's multiples of the half-life that really matter. And that's well, it gives you a good rule of thumb, a good understanding of how things are working. Okay, so that's the first order case. Now we're going to do the second order case, which is really no more complicated than the first order case. Let's go through it. I'm going to switch over to the other side here briefly. So here's the second order case. There's really two subcases within it. Both of these elementary reactions are second order, right? This one has two A's colliding with each other. This one has two different molecules, A and B, colliding with each other, but they're both second order. The first case, case 1 here, gives rise to a set of rate relationships or rate equations that has a second order term on the right-hand side, and then a set of relationships between the rates of buildup and the rates of decay for the reactants and products that we can also use. The other case is more complicated. There's two rate equations, right? One for each reactant here, A and B, and there's actually one for the product as well. And then there's a set of two relationships, or a set of relationships among three different rates. And so this case is more complicated. We'll go through it when we come to it. Let's deal with the simpler case first, which is this upper one here. All right, now I'm going to switch back and we'll do some actual details here. For the second order case then, we have the following. We have minus dA dt is equal to k times a squared. That's the rate equation proper. But then we also have this relationship, dA dt minus dA dt is equal to plus dP dt. And that just follows from the stoichiometry of the reaction. Let's integrate these two guys first so we can get some basic relationships. If we just integrate both sides, so minus the integral dA dt dt equals the integral dP dt, then that gives us that a on this side minus a on this side is equal to p on this side plus a constant of integration. And so we get that a, switching this over here, plus p is equal to some constant, which we don't know at the moment. But if we evaluate both of these at 0, at time 0, and if we say that there's no product present to begin with at time 0, which doesn't have to be the case but is usually the case, then we can see that the constant just has to be a0. And so we overall have that a plus p is equal to a0. I did a similar kind of thing, not exactly this same thing, but similar kind of thing for the first order case up above, but I thought I'd go through the steps a little bit more systematically this time, so in case anybody got lost on that first example. There's a similar set of relationships for the more complicated second order case that we're going to go through in a minute, and for every other case that we go through, no matter what order, no matter how complicated. There are either a relationship like this or a set of relationships like this in every possible case. All right. So that's just accounting for the relationships among the rates. Now let's look at the rate equation itself. And so solving that, we have dA dt is equal to k times a squared. That means that dA over a squared is equal to minus k dt, integrating both sides, the integral from a0 to a, dA over a squared is equal to minus k, the integral from 0 to t of dt. Integrating this side, we get minus 1 over a, evaluated from a0 up to a, is equal to minus k, now integrating this side, times t. Minus signs cancel, and plugging in the limits here, we get 1 over a minus 1 over a0 is equal to kt, or the final, well, one of the more useful relationships, 1 over a is equal to 1 over a0 plus kt. We'll use that one as it stands to get the version of a linear plot for this particular case. But if we want to solve for a itself instead of 1 over a, then we get that a is equal to 1 over a0 plus kt, and that's maybe, in some ways anyway, the more useful relationship. Actually, both of these are pretty much equally useful. All right. If we plot, we need p still, so we have that p is equal to a0 minus a. And so let me just write down from the other side over here this relationship. We get that p is equal to 1/2, this is after some algebra obviously, a0 of k times a0 times t over 1 plus k times a0 times t. All right, so now we have relationships for both A and P, reactants and products. And if we're to plot them, we'd get something like this, starting from A0 at time t equals 0. We get a decaying curve. But it's not an exponential curve anymore. It's a different shaped curve. We can't tell that just by eye usually, so the question immediately arises, how can we tell? And we'll come to that. And then if we plot p versus time, we get something that's also just a rising curve. So again, qualitatively it looks very much like the first order case, but quantitatively they're different. All right, so how do we tell? One way is to make a linear plot. And we use this relationship up here to make that linear plot. If 1 over a is equal to 1 over a0 plus kt, and we identify that as y, this as m times x, and this as b, then you can see that plotting 1 over a versus t here should give us a straight line. And so 1 over a versus t should give us a straight line. The slope should be equal to k, and the intercept should be equal to 1 over a0. So a plot of 1 over a versus t is diagnostic for a second order process. Remember that a plot of log a versus t was diagnostic for a first order process. And now we've got a diagnostic plot, an equivalent diagnostic plot for a second order process. If you plot something other, if you plot 1 over a versus t for something other than a second order reaction, for a third order reaction, for a first order reaction, for a half order reaction, anything else, you'll get a curved line here. And that will tell you that it's not really second order. Again, as I said before with the first order case, in real situations you've got some instrumental noise, some experimental noise, and you can't always tell if something's truly a straight line or not. But if it looks like a straight line for a 1 over a versus k plot, then you have evidence at least, good evidence at least, that it's a second order process. All right. That leads us to the next case, to the complicated case, and this is among the more complicated things that we're going to do, so I'll go through it, hopefully fairly carefully. In this case, we have the reaction A plus B goes to P with a certain rate constant, and that means that first of all there's a relationship amongst all the rates associated with these different species, right? There's minus dA dt. That has to equal minus dB dt, and that has to equal dP dt. And if we integrate these, there's pairs of them here, right? There's this pair, there's this pair, there's the A and P pair, so there's 3 different pairs we can integrate together. And if we do that, let's just take this case for first. If we integrate both sides, we get minus the integral dA dt is equal to minus the integral dt, that is, dB dt, and that gives A is equal to B plus a constant. And now shifting the B over here, we get that A minus B is equal to a constant. And now again at time 0, both of those are the initial concentrations, so that must be the constant. So we get A minus B is equal to A0 minus B0. And now rearranging, I'm going to move the A over here, I'm going to move the B over there. I get that A0 minus A is equal to B0 minus B. And that last step there is just to make things a little bit easier, but that's my final form anyway for this relationship. And what it's saying is, look, it's saying this is the amount of material that the A lost, right? This is the initial amount, this is the amount we have now. So this difference is the amount that we lost. And this is saying that that has to equal the amount that B lost, which is just saying the stoichiometry of the reaction up here, right? Whatever you lose in A, you've got to lose a B as well. And that means that whatever you lost of A, you also lost for B. Likewise, on the other side, the amount you lost from A has to be the amount you gained from P. And so if we were to go through these other possible relationships, we're just going to get that same kind of stoichiometric relationship. And so let's just write them down. It's going to mean that P is going to equal to A0 minus A, right? That's the amount that A lost. It's got to equal P. And that has to also be B0 minus B, which is the amount that B lost. So we now have a set of relationships among the concentrations that we can use in the rest of our investigation here. What was I going to say? Well, anyway, we'll come to, there was something else I needed to say there, but now I can't remember. But anyway, we'll use these relationships as we're going along. Notice they just kind of make common sense. You can almost, well, lots of times people, after they've got a little bit of experience, can just write these things down from scratch. Don't need to go through all this complicated logic. All right, now we have to solve the differential equation. There's really two differential equations we could solve. We can solve minus dA dt is equal to K times A times B, or we could solve dB dt is equal to K minus dB dt is equal to K times A times B, or we could solve dP dt is equal to K times A times B. All those things are true, but you notice this relationship, you notice these are all the same over here. This set of relationships is the set of relationships that we had up here. Where is it? This set of relationships. So we're just repeating what we've already done. That means we can ignore these two. Let's just focus on this one and solve it. So minus dA dt is equal to K times A times B. And there's an immediate problem, right? We have A on this side and A there, but then there's this extra variable B. We've got to eliminate that, right? We can only have a differential equation. We got one differential equation here. We can only have one unknown. We can't have two unknowns. But we have this relationship up here, this one, which gives us B as a function of A. We have that B is equal to A minus A0 plus B0. And so we can plug that in there, and now we have a differential equation that only has one unknown. So dA dt is equal to K times A times, putting all this stuff in for B, A minus A0 plus B0. And now, following your book, I'm going to call this quantity plus delta, just to simplify the amount of writing I have to do. So minus dA dt is equal to K times A plus delta, and that's the differential equation we actually have to solve. Separating the variables, we get minus dA over A times A plus delta is equal to K times dt, and now we integrate both sides as always with these variable separable differential equations. Very easy. We get dA over A plus delta equals the integral from 0 to t of K dt. This is just equal to KT on this side. And now we have to do this integral. It's a standard integral. You can look it up in tables. There's a standard algebraic trick for doing it. I think I won't go through the tricks. Let me just write it down. That integral is of the form dx over x times x plus delta, and that is equal to 1 over delta times log of x minus log of x plus delta. So x here is A, so that becomes 1 over delta times log of A minus log of A plus delta is equal to KT. That's our answer so far, and now there's a bunch of algebra to do, and it's not illuminating or useful to go through it. It will take a bunch of time, so let me just write the answer down. It's over here. here is a worked out answer. Actually, let me just copy all these answers and come back over here. There they are. And so, looking at these formulas, you can figure out what they're saying, and we could spend some time doing that, but I encourage people to do that on their own. But let me just point out one thing, and the very first thing to notice is that as we're going through all these examples, they're getting progressively more and more complicated, and the expressions that we're getting out from solving the differential equations are getting more and more complicated. We're going to see that continue because there's still more complicated cases coming above, but at some point they become more complicated than they're worth, and it starts becoming more worthwhile to just do things on the computer. And that's what happens. For very complicated cases, people just do stuff on the computer. And you look at the answers rather than at these integrated rate expressions, which become hard to understand as the cases get more complicated. But we can notice this, that here's an exponential here in kt, which means that as time increases, this exponential is going to go up exponentially. It's going to get bigger and bigger and bigger. And it's in the denominator, which means that a is going to get smaller and smaller, which means that as we plot a versus time here, we're going to start at a0. Notice that if time is equal to 0 here, this is all just a 1. That gives b0 over a0 minus 1. If we work it all out, then that's just going to be equal to a0. And then things are going to decay away with time after that. Notice also that according to this relationship, b is just a constant offset from a. So if we started here with b0, there's a constant offset between those two, and that offset has to stay the same at all times. Sorry, I need to change that. So this goes down like this, and then there's a constant offset. Let me draw it better. I have it over here, but let me draw it a little better. All right, I drew it better over on this other side. Let me point it out. Let me just go there, I guess. Here's what it looks like. There's a constant offset between the two curves for A and B. And likewise, for P, there's a constant offset, which is A0 here, but also with a minus A, right? So wherever A is decreasing, P is increasing, and that's what we're seeing here. Okay. So there's 3 different curves for 3 different species. Notice that if we started out with more A than B, then the A never goes away. As time goes to infinity, all that happens is that the A concentration goes to an amount which is A0 minus B0, and that's because A is an excess reagent in this case, right? All the B gets used up, that stops the reaction. No more A can be used after that. We're out of B. And so as time goes to infinity, A doesn't go to 0, it goes to some constant amount, which is the excess that it started with. On the other hand, B does go to 0, at least in this case where we started with less B than A. I mean, you could reverse the two, right? You could have started with more B than A, and then everything would be reversed. But in this case, we started with more A than B, and so the B does go to 0, and the P concentration can never be higher than the amount of B concentration that we started with, right? Because you need a B in order to create a P in the first place. All right, so that's the third case, or case 2 of second order reaction. That's the most complicated case we've dealt with so far. And more complicated cases are coming in the future, but we'll deal with them as we get to them. All right, that leads us to a topic that your book doesn't really properly ever address, and that's a weakness in the book. I think it deserves some attention, and I think we need to talk about it a little bit in order to go very much further. We're going to deal with more complicated cases next, and that's going to require that we write rate equations for mechanisms, for entire mechanisms. And that means we need to talk about how that actually happens, what the rules are for that. So let's consider this this mechanism for the water forming reaction down here. So this is, I think I don't need this pane over here, so I can make this big. This is the mechanism for the water forming reaction, as I said a minute ago. Or at least it's our example mechanism for that. And it's got 4 different steps and 6 different chemical species, right? So H2, O2, H2O, those are the majority species, and then O and H and OH, those are the intermediate species, but all 6 of them will change with time. There's a rate equation for each one of those 6 species. And what we want to do is now write rate equations. So I don't have very much space over here, but let me write here. D, let's say we want to write the rate equation for the intermediate O. What is that rate equation? Let's see why that's not so obvious. First of all, O appears here, and it also appears here. It appears in 2 different rate equations. This rate equation is going to create O. This rate equation, or this elementary reaction, is going to destroy O. And both of them are going to contribute to the total amount of O that I have at any moment in time, and the rate at which it appears and disappears. And so this rate of change for O should have contributions from each of these 2 elementary reactions, and that turns out to be true. And what are those contributions? How do we write those contributions? That's what we're going to talk about. So rates of reaction, or rates of change for each of these species, all involve several contributions. Just to look at one more example, let's look at H here. The rate of change for H should be affected by, first of all, this first reaction, right? Because H's are created there. This second reaction, H's are destroyed there. This third reaction, H's are created there again. And also the fourth reaction, H's are created there. So H's are created or destroyed in each one of these 4 reactions, and that means there's going to be 4 contributions to this overall rate for H, and we got to figure out what those are. Down here, I guess I'll just leave that. I have an example of that for H2. So here's the rate of change for species H2 using our standard example mechanism for the water forming reaction. And let's look at what those contributions are. So here's the overall change, rate of change for H2. There's going to be a rate law associated with that rate of change that comes first of all from this first reaction, because H2 appears there, right? We go looking through the mechanism for places where H2 appears. Every one of those elementary reactions is going to contribute. There's going to be a term. You can see there's one from this reaction, that's this term. There's one from reaction 3 here, that's this term, and there's one from reaction 4, that's this term, because all 3 of those reactions involve H2. There's no term from reaction 2 because H2 isn't in that reaction. All right, for reaction number 1, the term is just the rate law for reaction number 1, right? The rate law in this case is K times H2, and that's what we have here, with a minus sign because H2 is disappearing in this case. So when the species whose rate we're looking at is a reactant, that means it's disappearing. That means it gets a minus sign, and that's the minus sign that we see there. Notice also the products don't appear. The rate laws for elementary reactions involve only reactants, and so the products of the elementary reactions are not going to appear in any of these terms. Only reactants appear in the rate laws for elementary reactions. All right, so for the next term, which is coming from reaction 3 down here, we have a rate law term which has got a minus sign because H2 is a reactant. And the rate law involves the reactants, and there's 2 of them. This is a second order binary collision, so oxygen and H2 appear, and then the rate law for reaction 3. So the minus sign, the rate constant, sorry, and the two concentrations for the two species are all in that term. And then finally for reaction 4 down here, the third contribution, again, H2 is a reactant, so there's a minus sign, the rate constant for reaction 4, and then the two species, OH and H2, complete the rate law. All right, a couple of comments that need to be made. First of all, this overall mechanism doesn't have any reversible terms. But some mechanisms do. So for example, we might see something that looks like this. A plus B goes to C. That's two elementary reactions. It's not just one. So here there's two different rate constants here, K1 and K minus 1. It's traditional to write it this way with two arrows going back and forth, but that's really A plus B goes to C with rate constant K1, and C goes to A plus B, the backward reaction, with rate constant K minus 1. So if you see a reversible step like this, immediately replace it with two different elementary reactions, and then you won't have any trouble with it. That's just a warning. Another example that I want to look at down here shows a subtlety that doesn't really show up very much in this example that we did above, and that has to do with stoichiometric coefficients like this 2 here. So I have another, this is just a fake example, it's not a real example, but I've got two A's plus a B forming a C. That's a third order step, notice. You won't see any third order steps like that in real life, but I put one in because it helps illustrate this issue. What's the term? So if I'm writing the rate of change for A here, A appears, so reaction number 1 here is going to contribute. What's the rate law that's going to contribute for this case? Well, first of all, you're going to get, since it's a third order step, you're going to get an A squared, right? That's from this 2, and a B in the rate law for this elementary reaction. But then, because the A's are disappearing at twice the rate as either the B's or the C's, you've got to put that in there also. So this 2 that appears as the stoichiometric coefficient appears in two different places. First, as a power in the rate law, and then also as a prefactor in the actual overall term. Down here, for example, A appears again, this time as a product, so it's got a plus sign over here in the third term. And now, because it's a product, it doesn't appear in the rate law, just D and B do here. But 3 of them are created every time a D or a B disappears, and so we need to account for that, so there's a 3 that appears in front. And that's generally true. Whenever the species whose rate you're keeping track of has a stoichiometric coefficient that isn't a 1, then you need to put that stoichiometric coefficient in front of the rate law, in front of the term that's accounting for the rate. All right, down here, I've written out all 6 of the rate equations for all 6 of the species that are present in this example mechanism for the water-forming reaction. I won't go through all these things in detail, it's just more and more of the same, but I very strongly suggest that people do that for themselves. Here's the answer, here's a problem I'm posing for everybody. Go through this mechanism, write down the rate equations for each of the 6 species involved, and then come back and look at this set of answers that I've written and see if you get agreement, and if you don't, then ask some questions. And with that, we are ready to start talking about what are called simple reaction mechanisms. We've kind of been talking about simple reaction mechanisms already, but these are a little less simple and a little bit more illustrative because of that. But we'll save that for next time.